Our next speaker is Espen Tallaksen from EmLogic, the CEO, based in Norway. Espen is the author and architect of UVVM, the leading verification methodology and library for VHDL, and giving us presentations at various international conferences with great feedback. And he's also doing courses on FPGA design and application. So, thank you, Espen.
Thank you, Mike. So, I guess you can all hear me?
Yes, we can. Thank you.
Yeah, good. So, I want to use this opportunity to talk of something I think is a really serious lack of verification knowledge. So, the title here is lack of an important verification knowledge. But this is even more important if there is a corresponding lack of design knowledge. So that's a really bad combination. And the subject of this presentation, the cycle-related corner cases, is indeed a design and verification challenge. But I'll talk about the verification part here. So what is a cycle-related corner case? This is something that occurs when the cycle in which an event happens is not fixed, and this event is related to another event. And typically events in different state machines or any interacting flip-flops really that affect each other or affect the same objects. For example, that could be any two or more events combining into a state machine. One example could be an interrupt controller receiving two interrupts at the same clock cycle, or it could also be a problem, a corner case for the case when you have two interrupts occurring 1 or 2 or 3 cycles apart. That depends on your design. It could also be any communication interface. I'll come back to that in a later slide, where you typically have a readout versus new data entry, and lots of other scenarios. And the main problem is that these are very often not seen or detected by the designer as a corner case as such. So let's look at this communication interface example. This is code here, but you probably understand it's pseudocode. So the case is if you're receiving, if the CPU is reading the RX data register, then you do something. Else, if you have a new byte received from your RX, then you do something. And this is an if and else for non-exclusive actions. So that means we have a bug if both of these are true in the same cycle. But of course, you wouldn't decide it like this because you see immediately that this will result in problems. But in a real life code, you will probably write this in many different ways. Like for instance, if you have a huge process, this is VHDL, but it applies to Verilog as well. So in one place in your code, you are checking for the read from CPU of this RX data register, then you do something. And then maybe 200 lines lower in your code, you are checking whether you have received new data from the RX. And of course, this is much more difficult to see and understand. And of course, you get a bug if this something is to go to a new state or assign to the same object, if both these ifs are true in the same cycle. So what's the probability of that? If you look at the design of a 100 megahertz, the clock design, you have a bit rate of 100 kilohertz, then you have a byte rate of 10 kilohertz. Lots of details, but this is just to illustrate the probability here. Because then you have a probability of a bug of 1 to 10,000 per byte. And the probability of detecting this in a sequential simulation for one single byte is also 1 to 10,000, of course. For thousands of bytes, it could still be the same in lots of test benches because you're basically doing this test the same way over and over again. And some test bench, you will have a higher probability of detecting this, but not necessarily much better. In a lab, it totally depends on the setup, but again, there's a high probability that you're actually repeating the same sequence over and over again and will not detect it. Of course, in the field, there's a high probability this will actually occur as a problem because that's more random. So how do we avoid corner cases? Well, most corner cases are given by specification and cannot be avoided. But some corner cases are also added by implementation. Some of these can also not be avoided, but definitely lots of those can be avoided, and we should try to do that. So it's only a problem when the design doesn't work for that case and it's detected too late. So it's all about detection, really. So let's look at detection for this case. First of all, I have to look at the awareness experience here, and that is generally very low, and that means we'll easily miss such bugs in most projects. If you do simulation properly, you can detect all of these problems, but experience is extremely important, and how you approach this is important, and you need to have a good test bench architecture where you can skew the interfaces with respect to each other. I'll come back to that. Review, of course, can detect this. It's really important in any way, but it's really complex as well. Lab tests, I mentioned that. Lots of test cases are possible, but you will very seldom test for cycle relations, and it's often restricted by application software. So basically, simulation is the way to detect this. So how can you do that? This is an example from UVM using a test sequence and verification components. And thing, as I said, we have to skew one interface access with respect to another to actually hit these corner cases. And this is also an example from UVM, where you can see doing a UART transmit into the RX or the device on the test, going into this RX register. Never mind the syntax here, but just saying a UART transmit, and you're doing that via this UART verification component, instance number 1 on the TX interface. And then you're reading the data out from the CPU interface. And in this case, is this SPI checks. SPI stands for Simple Bus Interface. It's basically just a register interface, CPU interface, and you're reading the data out. And in UVM, you can do this in parallel. That means, of course, in this case, that the SPI check is reading the previously received data. But the good thing about doing this in parallel is that you can do the UART transmit and SPI checks at the same time, or you can do as shown here, insert a delay so you can skew these interface accesses with respect to each other. At the end of this sequence, you can just await completion. That basically means that I'm now waiting until the UART transmission is completed before doing the next transmit. And then we can make a loop around that, and looping from n cycles before I assume the corner case is, and to some cycles after that. Of course, I might miss in my sort of interpretation and understanding where this corner case actually is. That's why we're doing a few cycles before and a few cycles after. But that means we can skew this, and we will hit this corner case within a few iterations, rather than, for instance, 10,000 cycles, or 10,000, sorry, iterations. So I want to sort of conclude by saying that there's a problem with awareness for cycle-related corner cases. If you look at clock domain crossing and value-related corner cases, people talk a lot about that. And this is basically showing, the graph is showing problem awareness versus solution awareness. And you can see that most experienced designers are definitely aware of the problem, and quite a few also know how to solve them. It's a bit more difficult with novice designers. But if we look at the same for cycle-related corner cases, there is so much less awareness on both the problem itself and definitely also on solution. And that is a huge problem, because occurrences, error probability, and severities are definitely comparable. So, conclusion, most corner cases are given by specification, and we should avoid adding more corner cases by implementation. We should make sure to verify all corner cases by simulation, because that's basically the only way you can control this and detect these problems. But there is a serious lack of awareness and knowledge on cycle-related corner cases. We need a verification system that can hit cycle-related corner cases. So yes, I mean, a corner case might not be a problem in itself, but it's always a challenge, because we have to check it out. And without sufficient awareness and attention, a corner case could definitely be a major problem. And again, we need far more awareness on cycle-rated corner cases. So with that, I'm finished with the presentation. I just want to also mention briefly that we're maintaining the UVM, we do courses, and also want to mention that we're doing actually a webinar for the DV Club on 28th of June on UVM for those who are interested. Thank you.